last time we covered context, free grammar, right? It's a way of describing, right? A set of describing a set of strings. So just like regular language, but this is more powerful. It can describe more, right? It can describe more. So we said, like, formally, this thing is a for tuple that includes sigma. That's your alphabet, right? All the possible strings. We write anything from here, we call it a terminal. And then you n, like, right, this for tuple is like you have sigma, n, p, and then with the start symbol, right? Let's say s. So n is the variables, uppercase, right? Usually uppercase letters. So the goal is eventually, right? We eventually rewrite variables with terminals. That's what we want to do. And then productions, right? We call it production. So production is usually you have a variable, right? Let's say a, and then goes to something, right? It goes to A0, then you can recursively, you can rewrite, right? Anytime you see an A, you can rewrite with A0. That's a production, right? And then start symbol. S is going to be start symbol. So that's where you start, right? You start from this starting point. So I'll give you an example. That is, let's say, write CFG that accepts all palindromes over AB. So what is that? Cool. So we accept, right? Accept, that is A, accept, AA, accept, A will accept, AA, we accept, AAA, we definitely accept, ABBA, we accept, BBB, we accept, right? Like that, like that. So if it's a palindrome, then you accept. We reject ABB. So this is not a palindrome. So the idea is, if you start from S, right, and then do multiple steps, you just apply this production rules, right? And then after multiple steps, if you can produce a string S, right? Let's say ABA, if you can produce, right? If after multiple steps, if you can produce or generate ABA, then ABA, come on, belongs to this language. That's a whole concept. So for example, if I write this grammar, ASA or BSB or B or A or epsilon. So now this context-free grammar can generate all the possible palindromes over the alphabet of A, B, right? So let's generate A. That is S goes to A, right? I'm going to just pick this rule, right? You can pick any of these production rules. So I rewrite with A. That is simple. So AA, then that AA, what do? S goes to ASA. Good. And then the next time, S goes to, right? S goes to epsilon, then it will become AA. That's what I do. Another one, ABA. So ABA, how to generate ABA? S goes to ASA, and then again S goes to B, right? Then it'll be ABA. So this process, or definitely this step, this S has to be replaced by B. If you replace with A, then it generates a different thing. ABB, right? No matter what you do, you cannot generate it, right? S, starting from S, you cannot generate, right? There's no way you can generate ABB. So then ABB does not, right? So I stop here. ABB does not belong to this language. Okay. So this process, starting from S, right, finding a string, that process is called derivation. So you have to find this derivation, right? Because it's a specific steps to generate a string. This is called derivation. Finding that derivation, it's called parsing, right? Finding a derivation is called parsing. So we have to, right? So parsing algorithms, what does a parsing algorithms do? If you give me a context-free grammar, if you give me a string, the parsing algorithm will tell you how to do these steps, right? How to follow these steps and generate that string. If you can't, then that string doesn't belong to this language. So same thing, like last time. You start from S, and then eventually if you generate this Java program, then this Java program belongs to this Java language. If you can't, because, right, if there's a missing, semicolon, and then you cannot generate this language, then there's a syntax error, right? If let's say int main int a, and then close. So this does not belong to a C language, right? I mean, if there's a semicolon is missing, because there's no way you start from the S. Somehow, if you say variable declaration, that variable declaration ends with a semicolon. Then if the semicolon is missing, then you cannot generate. So this program, right, does not belong to my language. Okay, see. So that's it. That's a whole process. So all computer programs, if you give me a correct context-free grammar, I start from the S, and I can generate this program that belongs to this language. So let's look at some examples. We already did look at the palindrome, and I say, how about we all know regular expressions, so that'll be, how about this thing, right? 0 star, and then 1 star. How about that? So the alphabet is 0, 1. So the 0 star, 1 star, right? So this thing can, any number of zeros, after that, any number of ones. So that'll be S goes to AB. So it can be two variables. Now what is A? A is going to be 0A. So repeat 0 any number of times, right? Any number of times, and then you can stop at epsilon, because this can be nothing, right? You can repeat no times, 0 times. How about B? B, I can do the same thing. That is 1 B, and then what is that? Come on. Then stop at the epsilon. Yeah. So then this thing will generate, right? You start from S, and it'll be A. And then you repeat A any number of times, recursively, how many times you want. It's all A's, zeros, and then it's all ones. But definitely what you cannot generate, this is something you reject. That is 0, 1, 0. There's no way you can do that, right? Starting from S, right? Starting from S, you generate A right here. Once you go to B, you cannot go back to A, right? Look at that. You go, this is all A's, and then this is all, zeros, all ones. This thing you reject, okay? So this is language. So let's do another example. That will be, you had generate, right? You accept all A, B, C, D. A, B, C, D. Let's say same number of A's with same number of D's, and the same number of B's with same number of C's. How about that? So something you accept, that will be, right? I accept what? I accept A, D. Fine. I accept A, B, C, D. Fine. What is that? And then I will accept A, B, B, C, C, D. Yeah, I will accept that. I have same number of B's and C's and same number of D's. Or AA, BC, DD. I will also accept that. So, cool, let's do that. That is S goes to outside, right? AD. ASD, right? So that's outside. If you keep doing this, you have like AD, AADD, AAA, DDD. And then I will, when I'm done with the outside ADs, I want to come to the speed C that goes to T, okay? Then T goes to, that is BTC. See, this will repeat the middle BCs any number of times, but you have same number of B's and same number of T's in the middle. You can repeat any number of times, okay? Then, right, then I can stop at the epsilon. Okay, I can stop at the epsilon because this M right here, it said M is greater than equal to greater, no, greater equal to 0, N is greater equal to 0. So this way it can be, you know, epsilon. If I change it, I say you cannot have 0 number of BCs. You at least have to 1 or more, right? Look at that. You B and C, you must at least you have 1. Then, yeah, you cannot stop at epsilon. You have to stop at BC. So if you at least 1, or you can want more, right? You can repeat more, but at least when you stop, you have to stop at the BC. So this way, this AD you cannot accept, right? It has to be A, B, C, D at least. BC, fine, because I didn't ask. A has to be greater than 1, okay? So with all that, I'll take a question. Now, yes?
Before, you said M is greater than or equal to 1, you just said nothing.
If M is greater than 1, then yeah, nothing. Yeah, I can accept empty string. Yes, that's a good point. That is starting from S, right? If this is 0, then remember this is, like, let me write that. That's another grammar. That is, just copy this. So if this is epsilon, yeah, then you can start from S goes to epsilon. Yeah, fine. You can accept empty string. Empty string is epsilon. Yeah, empty string belongs to this language in that case. Another question? Yeah?
Does context-free grammar only say like yes or no, or can it keep track where down the line where it just fails or type of thing? Or does it say, oh,
Yeah, the whole context-free grammar just say, if you give me a grammar, if you give me a string, can I generate the string? Yeah, it'll give you, I mean, the parsing algorithm will give you the, derivation if you can generate it. Or if you can't, then it'll say, yeah, it can't. It's just to stop somewhere in the derivation. Yeah. Yes?
if you want to see like an exact number or like a
Exact number? Exact, like what, for example? Give me a.
let's say like you wanted to repeat 3 times instead of like M equals 3.
Then I say BBB. If If that n is any like specific number, I'll just write it, right? Like that, and then it's specific. You say, for this, m is equal to 5, n is equal to 10. Then you just do it, right? You can just write the long string as the terminals. Then, no more? Yeah?
Wait, so far, every time you've been doing it, you've been putting epsilon last. Does the order matter? Like, could you do like T? T is like epsilon or ET?
Yeah, for the same pipe, it does not matter. So here, if I have epsilon right here, and then this, it does not matter. But this matters. So like putting this before T, it matters because then the order can change. But in the same pipe, no. Actually, it should be this. I'm sorry, I this really, this case should be T goes to epsilon, T goes to, this should be like this. We simplify it by a pipe. Otherwise, each production can be a different new line. Now, yeah. Yeah, so it's up to you. Because the grammar can become big. I showed you this Java specification. Imagine that's why we want to put pipe so that it is shorter. But there's no difference whatsoever. It just says T can be replaced, right? You can rewrite T with all those things from the right. Yeah?
So, if you're using this in real life, to prove something to prove that a certain string isn't part of the language, wouldn't you have to try like every combination, like wouldn't you have to try infinite combinations of transformations?
No.
Like, how do you prove that something's not part?
Yes. So we have algorithms that terminates. Yes. Good question. So because this thing is recursive, there's an infinite number of choices. So there are algorithms. Just like we rewrite our NFA, DFA, you can rewrite this context-free grammar such that it will eventually terminate. That name is called what? Chomsky. He's politically very active. Yeah, that guy. He invented this thing. Yeah, Chomsky normal form. See, it's exactly the same. If you formal language theory context program, just say Chomsky normal form if blah blah blah. So if you transform your context grammar to this thing, and then it will eventually stop. Okay, Chomsky is a human language, the researcher, but because the same kind of concept, we apply this to computer programming languages. Chomsky normal form, yes. Good question. Anything else? Nothing. Okay, let's do the quiz. Go. 5, 4, 3, 2, 1. We will stop right here. Now let's see. This one says S goes to T, that is correct. T goes to AT, that is also correct. Now this T, there's no TAT. That I don't have that, right? How do you change from AT to AT, TAT? No, there's no production that does that. So this is definitely wrong. Second one, S goes to T, T goes to U. Yeah, fine. This is fine so far, but U cannot go to AU. This is wrong. There's no AU, right? So that is wrong. S goes to AT, and T goes to AT, fine. T goes to U, fine. U goes to CU. Yeah, this is good, right? I can definitely do that. Oh, yeah, S goes to AT. That is wrong. I'm sorry. Yeah, this somehow I skipped. Cool? So that is wrong. Now let's see our last one. S goes to T. T goes to AT. AAT. Yeah, this is it. I'm sorry. So then it'll begin with D. See what you did. D. This. Go. Okay, 5, 4, 3, 2, 1. Stop right here. So this one, you can generate any number of B's after that. If you have enough B's and you go to T, you can generate any number of A's. After that, you go to U, they can generate any number of C's. But once you reach to A, you can't go back to B. Once you reach C, you can't go back to A. So that will be the same. Any number of B's, A's, C's, but after C, you can't go back and get another, another A. So that will be it. So let's do that. Ah, that's very good, right? Very good. Cool. So these are some rules, right? If you have repeat 0 or more, 0 or more, so this is more, this is 0. If you say 1 or more, then this is a 1, and then if you want more, you repeat that, right? So this is A star, B star, then I just did 0 star, 1 star, that would be S goes to AB, right? S goes to AB, and then you individually do A and B, so that it's any number of this concatenated by any number of this. But after B, you can't have another A because this is the case. All small a's should show up before the b's, right? B's. This is the case, A and B n, then it will be ASN, right? Just ASB, sorry. So that you match. Anytime you generate an A, you also generate a B, so that A and B, the numbers, they match, right? They match, they have same number. If you want to generate for every single A, you have to generate 2 B's, right? If you have to generate 2 B's, then it'll be S goes to, A, S, B, B. So every time you do one single A, you have to do 2 B's, right? 2 B's. So this is it. So there are these kind of basic rules. If you have or, then you split, right? Split. So you can, this union, all this, right? Before or after, you say, okay, T will generate whatever this before, V will generate after. That will be the union, okay? That will be. So that makes it easier for you to design contextual grammars. But sometimes this is not straightforward, okay? It's not like just, build it. Some languages can be difficult, okay? Can be difficult. Cool? So we did all of these, right? We did all of these, but still we can try, just to repeat 0 or this, like S goes to A or B. A is 0A, epsilon, B is 1B, epsilon, right? Then it'll be this case. This thing, and now you should know this, 0S1 or epsilon, right? You repeat for any number of times, they match, right? And then when you stop as the epsilon. So those are the basic cases. So this is it, and then there's some examples, right? There's some examples for this case. You can generate 1, 0 or any number of ones, right? But you stop at the 0. So repeat any number of this time, you generate million B's, but when you stop, you have to stop at the 0. So this is all the numbers that is divisible by 2, right? Cool. If you end with 2 zeros, then it's divisible by 4. So those kind of things you learned in 216. 1 star, for the regular expression, for this exact same language, the regular expression would be this. So these are, because it's a simple cases, you can have regular expression. But the cases like this, you cannot have regular expression because regular language cannot describe this string, right? So you can't always generate. Wow. Go again. Okay, 5, 4, 3, 2, 1. I stop right here. It says any number of zeros and any number of ones. But you can have more zeros, but more zeros than ones. Okay, cool. Then This is definitely wrong. This is like it'll generate same number. But this thing, right, this zeros can be more. This is, it can generate same number, and then after that, you can also generate some more ones. That is wrong, because in this case, 1 should be less. In this case, I can generate the same number at least. After that, if I try any of this, then I have more zeros. That will be exactly that case, right? Exactly this case. This one just generates, you know, what, 0, 0. Okay, yeah. This one, you don't know, right? It just repeats, and then 1s becomes 2s. But for that, you can pick any of these, so you can't control the number. But then the answer is C, right? Probably that's what you did. Oh, 92%. That's good. Come on. So yes, this is the one, right? Cool? So now wake up. So the fun part is, you know, done. So now we come to the part that you have to pay attention to understand. So for example, if I have the smallest, right, smallest OCaml, that will be like this OCaml expression. This is we're using the BNF style. In the BNF, instead of arrow, they use this, right? But otherwise, the same concept. So I can have an identifier. So this is a variable. I can have a number, usually it's an integer. I can have addition, or I can have a let expression. So that's my language. This grammar describes this expression, right? Expression. So now we have to find the, right? We have to find the parser, the parsing algorithm, right? If you give me an expression, right? If you give me an expression, let's say 1 plus 2 plus 3, then how do you parse it? So that is E goes to E plus E. One of those E's goes to E plus E. Then each E will be picking one of these numbers, then it'll be 1 plus 2 plus 3, right? That process is called parsing, okay? Parsing. So we'll come to the topic ambiguous later. So this is my arithmetic expression. So if you want to have any combination of plus, minus, multiplication, any of those, this expression, this function, this contextual grammar can generate it. For example, I have A plus B times C, right? Minus A, anything like that, right? Any possible expression, this thing can generate it. Starting from E, you can just apply these rewriting production rules. You can, right? You can generate any valid expression. All these, right? Starting from E, you can generate all these. These are valid expressions. If something is invalid, D, I cannot generate because it doesn't exist in my alphabet. This is a function call. I don't, right? I can't start from E, generate this thing. Nope, nope. Not this, none of those, because these are invalid. They don't belong to this language, okay? So now you should understand, instead of A plus EA, I could give you the whole C program, and then definitely this contextual grammar can become a little bit longer that can recognize C. Then, yeah, start from E, right? If you accept that string, that's a valid C code. If you don't accept, then there's a syntax error, okay? Syntax error. Are we good so far? Any question? Am I doing too slow today? Yeah?
So does that mean that if your alphabet is like very large, you have to manually put every single possibility, or is there a way to shortcut it?
The what is long? The contextual grammar or the string?
Like if your alphabet is very big, so like let's say you have an alphabet of 26.
Yes. So the alphabet, usually it is big, right? So, for example, C alphabet, it has all the keywords like int, long, float, addition, multiplication, all those things that is a keyword, then that's a C alphabet. Usually that can be big, right? Can be big. And the parsing algorithm can be very complicated. So it is possible, right? It is possible. Remember, like at the very beginning, we listed some of those algorithms like LL. It's like left to right, from bottom up. Those algorithms, they have a different power. Some algorithms are complicated. They can recognize more context-free grammar. Some algorithms are simple, but they cannot process some kind of context-free grammar. So once you come to the context-free grammar, it's not like regular language, right? The algorithm could just fail. Even a string that you should accept, my algorithm could fail because it's not powerful enough. So the parsing algorithms, you know, they differ. So you learn more in 430, okay? 430. Cool. This is the next topic. That's a parse tree. So the parse tree is just to show that derivation path, starting from the root, right? The start symbol is the root. Every time you do production, then it'll add an edge, right? It'll add a node. That internal nodes are the variables, the leaves, right? Leaves are the terminals. And then if you read them from left to right, that'll be the string you wanted, right? So we draw the tree. For example, this is my alphabet, right? This is my alphabet. So I want to generate the string, right? Generate a string. I think that string is ACU, starting from S, AC probably. I want to generate A and then jump off U and then generate C. So I could write this derivation right here. And that tree, right? This is a tree that corresponds to that derivation. That is, S goes to AS. Now S goes to AS. This is called abstract syntax tree, so parse tree. Now S goes to T, right? I take this rule. S goes to T, and then T goes to U, because I don't want B, so T goes to U. That is, T goes to U, and then U goes to CU, right? And then U goes to epsilon. So now, look at all the internal nodes are variables, and all the leaf nodes are terminals. If you read them, put them, concatenate them together, AC epsilon, that's a string you want, right? You want. So what do? We take this context-free grammar, run this parsing algorithm, and then it'll generate this, right? It'll generate this tree. That is the, you know, the abstract syntax. That's the shape of your program. How you start from this int main and then just produce all these possible, you know, this derivations so that you can recognize this program, right? So let's do some examples. That's based on the grammar, the expression grammar I gave you originally. Now I can do, right, the grammar. That is, this very first one, E goes to A. That's simple. This one, E goes to E star E. That's this. And then E goes to A. This goes to C. So now it is A, C, U, right? All the leaf nodes. Then this one is E goes to E star E. This E goes to open paren, E close paren right here. Then this E goes to plus E. Now this is B, this is D. That is C times, this goes to C. So then it's C times B plus D, right? B plus D. So this tree can be huge based on, you know, if your program is large, okay? Otherwise, this is a parse tree, okay? This is a parse tree. That is all these examples. Is that fun? No? Not fun? Yes. So when you do the next project, yes, this will make sense and it'll be fun because you're creating a GCC, right? You're creating a new language. If you don't like the current languages, Java C, you can create a new one. You just come up with the right. You come up with a context-free grammar. You write your compiler, and then yeah, people will use it. Okay, people will use it. So the parse tree, the one we generated, it does include some extra information like this. Look at that. You don't really need it because you do this to do multiplication. You have to calculate this node. To calculate that, you have to do the addition. Automatically, you're doing the plus before multiplication, right? So you do not really need, right? You do not really need some of these nodes. So it can be simplified, right? So this is what we generate. This is a AST. This is a parse tree. Parse tree has some extra information that we do not need. So now you understand. You're not going to draw this tree when you write a program. This will be it. Let's say multiply variable A to variable C, or this is multiply variable C to whatever is the result of plus, that is variable B to variable D, right? So next lecture, you'll learn how to generate this thing in OCaml, right? In OCaml. Based on the contextual grammar, I will generate this AST, and then I can evaluate it, okay? I can evaluate it. Cool? So let's do one of these. You pick one, and then I will create the parse tree. Which one? There's no number. You can, let's say, 1, 2, 3, 4, 5. Pick one. 3? Okay, let's do 3. E goes to E times E. So because I have to do this. Now, this E goes to D. I have no choice. This E goes to E minus E. Then this E goes to paren E. This E goes to E minus E plus E. Then this is D. This is B. This E is going to be A. So now you put all these leaf nodes, that is D times, right? And then open paren D plus B, right? And then minus A. So that generates D times D plus B minus A. So this is a tree for this one. So the idea is, if I give you a string like this, you can generate a tree like this, and then you can run. We can evaluate it. So evolve function, right? It'll take this AST and then execute it, and then it'll give you the result. Okay? Which one? Bottom one? Let's do the bottom one. How about I give you 30 seconds? Come on, you do it, and then I'll show you. See if you do the same thing. That's how we learn. Yeah?
Can you do that from right to left?
Yeah, I can do that. I can start from any side, right? Back. Yes. Yes, that's the next slide. That's a good question. Tree decides, your parse tree decides how you evaluate that. Precedence, the association, right? All those things. The tree will decide that. Okay. So now you're ready? Let's do that. You cannot take a picture and submit, right? So let's do it together. That is E goes to, right? Yeah, I start from here because he said, right? He asked, can you do from other side? Why not? E star E. So this goes to D, and then this E goes to E plus E. This E goes to A. This E goes to paren E. This goes to E minus E. This goes to B. This goes to C. So it may be a different tree from yours because I start from the back, but otherwise this is also mapped to the exact same expression, okay? So if you have a different tree, then it's possible. Actually, this is a good exercise. So now let's see how to make it same. So if you, right, every time you see a variable, if you replace the very leftmost variable first, that's called the leftmost derivation. If you do the rightmost variable first, that's called the rightmost derivation. This way, we have like uniform, right? You start from left or right. So then you have same kind of tree. For example, if you have SAB, you have to replace A, right? Any non-terminal before B, right? You have to replace anything before B, right? Then you replace B. That's called the leftmost derivation. So A goes, then this is like AB, and then you do B. If it's a rightmost derivation, just the opposite. You have to replace B, then you come to A. That's called rightmost derivation, okay? Rightmost derivation. So there is an example. I want to generate ABA, right? Starting from S. So S goes to, if it's a leftmost derivation, you have to replace this S. If it's a rightmost derivation, you have to replace this S first. So leftmost, I will replace this colorful S with A. After that, I'll replace this S with A, right? If it's a rightmost derivation, yeah, I have to replace whatever from the right, and then I do this, right? ABA. So now, this is these two things, right? These two things, look at that. It maps to the same tree. So from the tree, you cannot tell the difference. If you use this tree, you can't tell you did the leftmost derivation or rightmost derivation, okay? So each parse tree has a unique leftmost or rightmost derivation. If, right, we'll come to that. So it's not unique, right? It's not unique. Somehow, for you, it is possible that if you can do the leftmost derivation in both cases, right? This is a leftmost derivation and this is a leftmost derivation. And somehow you end up with a different kind of tree. This is very wrong. This is called ambiguous, right? This grammar is ambiguous. It means, what that really means, you have this program, right? You have this program. If you compile it with GCC, it generates 5. If you compile it with Clang, it'll generate 6 because they change this evaluation order and they both think they are correct. Because they're correct. Based on your grammar, I can do either this or that. Look at that. Let's look at the left. This one, it did the very first S, right? Then it became AB. And then the second S, it took this rule. It's still doing leftmost derivation. That's how it ended up AB, ABA. So this rule, this production, like this derivation says, I'm going to replace this is same. But this time, right, the very first S, right, the very first S, it didn't took this A, right? It took this one called SBS. And still it ended up as ABA. So the tree is, there are two different trees. I'll say that again. If you use leftmost derivation, it somehow can generate two different trees. This grammar is ambiguous. That is, I saw a girl with a telescope. So it depends how you understand it, right? This girl is, I use the telescope to see the girl, or this girl has a telescope. So this example I just copied from a real natural language processing class. This thing is ambiguous, right? Same thing as a computer program. If the computer program is ambiguous, then different compilers, they can translate it differently, okay? So if you have multiple, right, you could have multiple parse trees. So for example, this is not ambiguous, this is ambiguous. Looking at the grammar, checking if that thing is ambiguous, that's a difficult problem. But most of the cases will give you a simpler example so you understand, right? When you look, you know this is ambiguous. So this is also ambiguous. For example, let's look at the last one. That is S goes to SS, paren, and S, right? We want to generate these three strings. This is the very first option. S goes to SS. I took this rule. And then because this is the leftmost derivation, the very first S, right? Very first S goes to SS again. So now I have 3 S's. And then each of the S will become as this paren, then that's this case, right? It is still a leftmost derivation. I'm going to do another derivation that is S goes to SS. But this first S, originally, you replaced with SS. Now, I'm not going to do that. The single S, I will replace it with, rewrite it with this rule. And then the second S, now I change it to SS, and then I'll generate 2 more. So in both cases, I generated these 3 parens, but the tree is different, right? In this case, for this derivation, this is my tree. For this derivation, this is my tree. If you have two different trees, what could be the problem? We'll see that now, right? We'll see that now. So if this is my grammar, this grammar is ambiguous, right? This expression grammar is ambiguous. What can go wrong? So let's do this example, right? It is ambiguous. It will go wrong. I'm going to do this ABC, right? I'm going to do this ABC. That is, one derivation could be E goes to E minus E. That the very first E goes to A, then I have A minus E. Now the second E goes to E minus E, that is A minus E minus E. Then this first E goes to B, second E goes to C, then I have A minus B minus C. Very cool. I can also do goes to E minus E. Then from this, the very first E goes to E minus E again, that's E minus E, then E, right? Then from this, then first one goes to A, second one goes to B, third one goes to C. So this is my number 1, this is my number 2. Let's draw the number 1. That is, E goes to E minus E. And then this goes to A, this goes to E minus E, this goes to B, this goes to C. So this is saying A minus B minus C. Now, this is my second grammar. E goes to E minus E. And then the first one goes to, again, E minus E. In both cases, I am doing leftmost derivation. And this goes to A, this goes to B, this goes to C. This corresponds to A minus B minus C. Imagine if this value is 1 to 3, right? Then you could, right? If this is a 1, 2, 3, then you have 2 minus 3 is minus 1. 1 minus minus 1 is 2. In this case, 1 minus 2 is minus 1. Minus 2 is minus 3. In both cases, they are correct. They just parsed it based on your grammar. What was the problem? The problem is your grammar. Your grammar is ambiguous, right? This is, I saw a girl with a telescope, right? I use a telescope. This, the girl is carrying a telescope. I just saw the girl on the street, right? She has a telescope. So this, it depends how you translate it. One compiler translated this way, the other one translated the other way. Look at this, right? This association now is wrong. This is right associative, and this is left associative for the minus operator. So now you saw the problem, right? If your grammar is ambiguous, you have problem. This is all that example I just did, right? So these are two different things, right? Two different things. So this, where you see this problem, this is called dangling if statement. That is, right? Now if you do not, what did I do? Come back. Oh, it came back. So look at that. How do you do this? You have to map this if to this else or this one. Somehow it has to be very clear. Like if you have if, else, the else will match to the closest if, right? Then this is correct. If you don't say that, oh, this could also be correct, right? Then if you translate differently, you could have a different result. This, right? Look at that. This one is mapping if, and then the else is mapping to the closest. This case, if is mapping to the else, right? This if is matching to this else, and then this if is just part of the very first if. Those two things can result like very different, result. I'm sorry. Let's do this quiz. Come on. So I give you a hint, right? Anytime you see something like this, you could replace the first S with something or the second. Like remember, it's E minus E. You can replace the left. You can replace, the right. So that will create this ambiguity. Okay? 5, 4, 3, 2, 1. Okay. I stop right here. Go. Very good. right? Very good. Cool. So ambiguity is bad. So these are the problems, right? So ambiguity is bad. It can bring all these problems. What do? You have to fix your grammar. Usually, right? Usually we rewrite it. So when we create this context-free grammar, we be careful so that it's not ambiguous, right? Sometimes as parsing programs, it's powerful enough to handle that, but most of the cases we rewrite it, right? Rewrite it. For example, so this is, right? This is a grammar that fixed that expression problem. Remember? E minus E was a problem. Now they replaced with E minus T. So you can only extend to the left. The T can only go to the number. So now if you have like, let me do that. Just ABC, right? For this example, let me do ABC. That is, if you have A minus B minus C, then I go to E goes to E minus T. Originally, both are E's. I could have option to replace this or this. Now I don't. The T can only go to C. Look at that. T can only go to C. So this is fixed. So my only option is replacing this E. So that is E goes to E minus T and minus T. So now this E goes to T. So this will become T minus T minus T. That goes to A minus B minus C. So if I do this, that is going to be E goes to E minus T. This E goes to E minus T. And this E goes to T, that's A, that's B, that's C, that is A minus B minus C, okay? So this is my only option. There's no other way. You cannot translate it any differently because this T is restricting it, right? Is restricting it. So this is how you fix it. This is one example where you take that ambiguous grammar, right? And then you fix it. This corresponding to left associativity, right? So this grammar is left associative. It means A minus B minus C, you have to A minus B first, and then you do C, okay? If you change this order, you say T minus E, then it'll become right associative. Then if you A minus B minus C, you have to do the B minus C first, okay? So that's, this is a left associativity, right? Look at that. So now it will expand to the right, but the left is fixed, right? This is one way of fixing an ambiguous grammar, okay? Grammar. So based on you go left or go right, your tree will expand to the right or the left, right? This is your shape of your tree. Cool? Now I have 20 minutes. Nah? Okay. I'm very optimistic. I have 5 minutes. I'll show you this problem. We should do multiplication first, but because this grammar is ambiguous, right? You could do this first or do this first, depending on how you translate, right? How you translate. So if you parse, right, E goes to, look at that, E goes to E times T. If you pick this rule first, right, if you pick this rule first, it may be correct. If you somehow pick this rule, then E goes to E times T. And E goes to E plus T. Then this entire thing became, right, look at that. You have to calculate A plus B before multiplication. That means it's like what you did, right, what you did, somehow you just add a paren here. That's what this thing corresponds to. You have to do this thing before the multiplication. That is wrong, right? That is wrong because you have to do the multiplication before the addition. So we have to fix this grammar, right? What are you going to do? Because they're all at the same level, so there is no precedence. Plus to multiplication, they have the same precedence. You have to split up, right? Something with a higher precedence, right? It has to stay closer to the, something with a lower precedence stay closer to the root so that you can do it later. With something with a higher precedence, it has to be farther away from the root so that you have to calculate them earlier, right? That's what we did. So this plus has a lower, right, lowest precedence. It will close to the root. and then multiplication has a higher precedence, and later, and then the numbers, that's the highest precedence. You have to just replace that number. So this is, right, this fixed it. If you go back, we print the slides, originally, this plus and the multiplication at the same level. That's why we couldn't differentiate between multiplication and the plus. Now we split so that, right, so that you do the multiplication before the addition. So this fixes precedence, right? This is a trick, right? You have to somehow rewrite your grammar, fix your ambiguity. Otherwise, I could, right? I could translate it differently. So that's it. So we learned like another cool thing, context-free grammar, right? That can describe programming language syntax, right? So for a given context-free grammar, we can generate a derivation to recognize if string belongs to this language. Next class, we learn parsing algorithms that can do this thing automatically. Okay? That will be it for today. I'll see you next week.